In chapter 4, we're looking at the properties of pure substances. In chapter 3, we did first law analysis, but if you remember, you were given the values of internal energy, enthalpy, etc. And in this chapter, we're going to be looking at how we determine those from temperature, pressure, volume, and mass, the properties that we can measure. So a pure substance is one of, like water. So if I look at water, it's the same whether it's a liquid, solid, or vapor. So in all three phases, it remains the same. And so this is what a pure substance is, and we'll look at water and a couple of refrigerants, and that's what we use as a model, but it's true for all of them. And what we're going to start off with is how we define that, and what you can do is look in the text or follow this, because you can stop this and look at it. What we're going to do is we're going to take a pot. So I'm going to take a pot. I'm going to have a cover on it. It's not a very good cover. Let me change that. And I'm going to have this filled with liquid. And we'll let the temperature be T is equal to 20 degrees C. And it's 1 atmosphere pressure. So you know that water boils at 100 degrees C, 212 degrees Fahrenheit. And so what we're going to be doing is providing heat here. So we're going to have heat go into this and increase the temperature of the water. As we increase the temperature of the water, it expands a little bit. So if we say this is state A, and then we're going to go over here to state B, and we'll see that this thing expanded a little bit. We still have 1 atmosphere. We have a liquid now, and T is equal to 100 degrees C. And it's expanded a little bit, B. We keep heating it now, and you know if you keep heating it, the water boils. So now we'll have steam and liquid in the container. An atmosphere. And now I have this is 100 degrees C, the liquid is, and the vapor is. So this is the vapor. This is the liquid, and they're both at 100 degrees C. So one of the properties of a pure substance is that when I have a vapor and liquid in contact with each other, they're at the same temperature, and they'll be at the same temperature and pressure. So this is a property of a pure substance. If I had a different type of substance, these could be at different temperatures. And so for a pure substance, liquid and vapor are the same when they're in contact with each other. This is one of the important properties of a pure substance. We keep heating it, so we keep the heat going. So we keep the heat going, and here we're still going to have T is equal to 100 degrees C, and all we have is vapor, and we say last drop. So by this, we mean the last drop of liquid has evaporated, and now it's filled with vapor, just like this vapor. And now if we keep heating it, the temperature will increase more, and we keep heating it, and the temperature will rise, and we'll be at state E. And it'll expand a little bit. So we have 1 atmosphere, continuing, E, and this is, we have T is greater than 100 degrees C. And so what we want to do now is, if you notice, the pressure remained constant throughout. So we have this constant pressure process throughout. And what we want to do now is draw a temperature-specific volume diagram. We're going to draw temperature-specific diagrams a lot in this chapter. We'll draw them a lot throughout the course. But now I want to look at what happened between A and B. Between A and B, I started off at 20 degrees C. Let me get rid of this. I started off at 20 degrees C, and we heated it up to 100 degrees C. And the specific volume increased a little bit. So I have a little bit, so if I start here at A, I'm going to go up slightly to B. It'll increase a little bit. And then what happened is I started evaporating this. So when I evaporated it, the temperature of the liquid and vapor, the specific volume increased, the temperature remained constant all through this process from B to C. And then we kept evaporating it from C to D. And the temperature still remained constant at D. And then we started heating it more. And here we had T was greater than 100 degrees C. And the specific volume increases slightly as we do that, it expands slightly. And so then we go D to E. And what we have is we have certain names that we associate with these points. So we call this a saturated liquid. That's the temperature at which it starts to boil. We call this a saturated vapor. So it's a saturated vapor, so any further heating would cause it to become superheated. This is in the mixture region. So we have a mixture here. This is a subcooled liquid. So T is less than T sat. So this in T sat here is equal to 100 degrees C. So we have that the saturated temperature is the temperature at which it boils. And here we have something that's superheated. So we have a superheated vapor at point E. And what we now want to do is we will use this. So this is for one pressure. So we did this for 1 atmosphere, 101.3 kPa. So we did this for P is equal to 101.3 kPa, and T is equal to 100 degrees C, which is T sat. So that saturated temperature is the boiling temperature. So now let's do this at different temperatures, at different pressures, and we'll see what's happening. And so now let's draw this TB diagram again. We'll do it for different conditions. So I'll do it for this pressure, for another pressure, for another pressure. And you'll see that these are the saturated liquid points. These are the saturated vapor points. And if I were to have a lot of pressures, I could hook those lines together, and I would have something that goes like this. Goes up to a maximum and goes back down. And so what I have here is a saturated liquid line. Saturated vapor line. And this point is called the critical point, and there's a critical pressure that would go like this, and this would be P critical. And this temperature is T critical. So pure substances are defined by their critical points. So each one has a unique critical point, and we can define what they are by that point. Now we can simplify this diagram and sort of declutter it a little bit. And so what we're going to do is declutter this and have it look a little more simplified. So we have TB, and basically we have something like this. We have this is our liquid region. So our liquid region is here, our mixture region is here, and this is your superheat region. What I'd like you to do now is open the book to table A5 and A6 on page 792 and following. So open book to A5 and A6, pages 792 to 795. You can always stop the video while you're looking for your book. So I'm going to recommend that at times you stop the video, open your book, and look at certain things, just as we did in chapter 3. So I do this in table A5, and you'll see that temperature is the first column. So T is the first column, it's in degrees C, and P is the second column in kPa. So in A5, the temperature is in even increments, so I could go in at 50 degrees C. I'd see that the pressure is 12.355. I could look up the specific volume V sub F, so this is your saturated liquid, and this is 0.001012, and V sub G is equal to 12.028. So you should just check to see that you can find these values. So this is finding the values in table A5. In table A6, pressure is evenly incremented. So in A6, it starts with pressure in kPa, and it gives the temperature in degrees C, and this is Tsat, just as this was Psat. So here, if I look at 50 kPa, I see that Tsat is 81.32. So this is the boiling temperature. So this is the boiling temperature of the water. And I have that V sub F is 0.001029. And V sub G is 3.2408. And so you use this table if you're given pressure, so you can have even increments of pressure. Table A7 is for the superheat region. And you'll notice that there are columns for pressure. So if I go to so here, I'll go to the pressure is 250 kPa. And you'll notice that there's a parentheses that says 127.4 degrees C. So beneath the pressure, it tells you the saturated temperature. So this is the temperature at which the water boils at 250 kPa. And we'll put in that for a temperature of 300 degrees C, I can look up the specific volume, and I'll just have V, because we're in the superheat region, there's no V sub F and V sub G, and V is 0.0518. So what you should do is make sure that you can find these, and then we're going to go through finding properties for how that works. So now let's look at the TV diagram and notice where V sub F and V sub G are. So if I draw a TV diagram, and I normally don't use colored chalk, but in this instance I will. And so if I draw a line of constant pressure, it'll go up, it'll go over, and it'll go up like that. So that's That's our line of constant pressure that we developed just a little while ago. And this value is V sub F. This value is V sub G. The difference between them is V sub Fg, and it's not a tabulated property. So V sub Fg is equal to V sub G minus V sub F. And so that's this distance right here. So this distance right here is V sub Fg. So notice now, so what I want to look at here is that temperature and pressure in the mixture region. So this is our mixture region. Temperature and pressure are dependent variables. If I know the temperature, I know the pressure. Just as I was here, if I knew the temperature, I knew the pressure. If I knew the pressure, I knew the temperature. They're coexistent. So if I want to find out how far along I am in this evaporation process, so the evaporation process is going on, how much has it evaporated, I need another property besides temperature and pressure. And within the mixture region, we have a property called quality. X. It is for mixture region only. So in the mixture region only, we have this, and X is equal to the mass of vapor over to the mass of vapor plus the mass of liquid. So it gives us the fraction of vapor that's there. And so if I start out at V sub F as a saturated liquid, I'll just say V sub F as an example. For a saturated liquid, there's no vapor. Therefore, X is equal to 0, because m of the vapor is equal to 0. And for a saturated vapor, there's no liquid, and so I have X is equal to 1.0, and the mass of liquid is 0. So X varies between 0 and 1.0. And so if it's in the liquid region, it's not defined. If it's in the superheat region, it's not defined. So now, let's go back and we'll look further and introduce this idea of quality. So let's do an example. And let's say that X is 0.6. And we'll do at T is equal to 50 degrees C, we have those values. At T is equal to 50 degrees C, V sub Fg is equal to V sub G minus V sub F. So you can look and you see those values. So we have 12.028 minus 0.001. And so I have V sub Fg is 12.027. And now let's look at what we're doing graphically. So let me show this graphically. Let's draw the TB diagram. And we're at 0.6, so about 60% of the evaporation is gone. So probably we're here. So this is where we are, and we'd like to determine the specific volume at this point. So if I look at this, it's equal to V, how do I get here? It's V sub F plus this change If I have 100% of the change, I'm over here at V sub g, I'm going to have x times V sub fg. So, not very good V sub fg. So I have x V sub fg is this distance. So when we look at this, I see that V is equal to V sub f plus x V sub fg. And if I substitute in the values we have, I have 0.001012 plus 0.6 times V sub fg 12.07, 12.027. And so we get V is equal to 7.217 cubic meters per kilogram. So I'm able to solve for the specific volume. What we can do is we can do this for all properties. So this isn't just true for a specific volume, it's true for internal energy, it's true for enthalpy, it'll be true for entropy. These are things that we'll look at. So now let's find the value for enthalpy at this condition. So you can look up the value of H sub f, H sub fg at these conditions. So at 50 degrees C, so we're still staying in table A5, we have H sub f is equal to 209.56, H sub fg is equal to 2382.7, and H is equal to H sub f plus X H sub fg. So 209.56 plus 0.6 times 2382.7. And we calculate that H is equal to 1639.2 kilojoules per kilogram. And so that enables us to find the enthalpy at this condition. And so we could do this for table A5 and A6. So A5 and A6 are where we use this. Now, let's look at the properties in the superheat region. A7, superheat. So if I look at properties there, and I know in the TV diagram, we're up here somewhere, and this is all the superheat. So this is all the superheat. So let's say that P is equal to 250, so we'll use the value we had before, 250 kPa. And we'll pick T is equal to 300, which we had also, 300 degrees C. And I can look up the value of enthalpy directly. H is equal to 3070.3 kilojoules per kilogram. And X is equal to not defined, not available, not applicable. And so we're looking at that, and that becomes an important part of what we're going to do. Now I'm going to give you some practice in finding values. So I'm going to give you some practice and give you some examples where you figure things out. Now, in terms of figuring things out, figuring out the steam state. So we want to be able to determine the steam state in, are we here? Where are we? So what you do is you always reference, so you're going to reference yourself to this value, the F and the G value. So you're going to reference value to the F value and G value. So if it's less than F, it's a subcooled liquid. If it's greater than G, it's superheated. Obviously, if it's in between, it's a mixture, and you'll have to find the quality or something like that. So now let's look for some of these problems. So let me write these down, and then you can work on them, and then I'll go over how to find them. So A, we're going to have P is equal to 500 kPa. Specific volume is equal to 0.123. And we want to find T is equal to what? Internal energy is equal to what? The quality is equal to what? So that's A. For B, we have P is equal to 2,500 kPa. T is equal to 300 degrees C. And we want to know what H is. For C, we have P is equal to 1,600 kPa. T is equal to 150 degrees C. And we want to find H and X. For D, T is equal to 140 degrees C. X is equal to 0.8. And we want to find P and H. And for E, P is equal to 1,000 kPa. H is equal to 3,110, and you want to find T. Now what I recommend is that you stop the video at this point, that you've transposed these into your notes, and you look these up and figure out where they are. What I'll do next is go over the solutions to what they are.